Okay, a few announcements before we start today. The couple of student organizations sent me flyers to advertise their meetings. So we have Delta Omega Chi has their 5th general meeting. They're going to have some sort of representatives from the new UH College of Medicine there. So that'll be this Wednesday at 5:30, right after our class. And then same day, I believe it is, so you have to choose between these two, Alpha Eta Alpha is having a health panel. So a Q&A session with a few different health professions represented. So if you're interested in that, the information is here. Now the other announcement that I was asked earlier today by a student in the other section to pass this along to you. So I know that many of you take the chem lab during the summer after this semester is over, because I know a lot of you didn't either get in this semester or just didn't want to fit it in. So the normal time that the chem lab is offered this summer is in the earlier summer session. So it'll start, I believe, in June and go through July or something like that. So and there's a whole bunch of sections available if you've already looked at them. There's a lot. There's some interest, though, in having another alternative Chem 1 lab during the summer session 4, which will be at the end of the summer, so from July to August. Currently, there's not a section available for that, but apparently if they can round up enough students who are interested, they need about 20, and they have about half of that so far. If they can round up enough students, they will open up a section during that second half of the summer. So if that works better for you, then you can contact Mohammed. He's a student from the other section. I didn't realize that they let students create new sections, but here we go. So if you contact him and say that you're interested, he will collect the list of names that are able to sign up. 'Cause they won't actually open up the section unless they have enough people to sign up, because it's fairly expensive to run a chem lab section with all the lab facilities and TA support that's needed. So they need at least 20 students to be able to do that. So if you're interested in that, the information is there, and just work that out with him. I don't really know all the details, but that's what I was told today. So today we are going to basically finish Chapter 8, which is the section on gases. So we're getting close to the end. We have this chapter to finish up today. We have a few lectures on Chapter 9 that we'll kind of spread that out, because there's several different topics in Chapter 9 that aren't all that closely related to each other. And then we'll be moving on into final exam review. So we're getting, as I said, close to the end with only a few weeks left. So what we're going to do today to start out with, and for most of today really, is talk about gases at the atomic level or at the molecular level. So even though your textbook is an atoms first approach, for this particular chapter we actually didn't do it that way. We did sort of the macroscopic gas laws first, relating pressure, volume, number of moles, and temperature. And then now we're going to talk about how the molecular and atomic behavior of gases relates to those gas laws that we learned. Okay, so we're going to get into that today and talk about how we can sort of rationalize various aspects of the ideal gas law with the proposed behavior of gases at the microscopic level. So this is referred to as the kinetic molecular theory of gases. Kinetic refers to motion, so a big part of this is the motion of gas molecules that we'll talk a lot about today as well. So there are a few postulates of this kinetic molecular theory. The first is that we know that gases are made up of atoms or molecules, depending on what type of substance it is, and those particles, the atoms or molecules that make up gases, their volume is assumed to be 0. Now we should recognize right off the bat that this isn't true. We know that atoms and molecules have some size associated with them, but for this ideal treatment of gases, that's assumed to be 0. And so essentially you can think of gas particles being, again, atoms or molecules that make up the gas. They are essentially thought of as point masses. So a common misconception, this does not imply that they don't have mass. So gas molecules still have mass, but they don't have any volume associated with them. So they're what we call point masses. Non-zero mass, but a 0 volume. And what this is essentially saying is, it might sound ridiculous to say, wait a minute, we can't just assume that atoms and molecules have no volume. But what it's essentially saying is that in a sample of a gas, the atoms and molecules are spread really far apart from each other. So the volume of the gas molecules compared to the volume of the container they're in is extremely tiny. So especially at normal pressures that we work at, close to atmospheric pressure, not too much higher than that, there's a lot of space in between the individual gas molecules in a sample of gas. So you basically assume that the volume of the container is much, much, much larger than the volume of the molecules themselves, or you assume that the molecules have 0 volume for this to work. All right, the other part, which again deals with the important aspect of them being in motion. So these gas particles are in constant motion, and it's random motion. So there's no directionality to how they move. They just move in a straight line and then they collide with something and change direction. So there's no real predictable motion here. But they're in constant motion. And what we talk about pressure a lot, right? Pressure is one of the key characteristics of gases that we introduced very early on in this chapter. And so when these gas particles are in constant motion, they are sometimes going to collide with the walls of the container, and that's what causes pressure. So it's collisions of the gas atoms and molecules with the walls of the container is what results in pressure being measured for gases. Actually, remember, pressure is a force over area, so anytime a moving object collides with the wall of the container, it exerts a force on that wall, and then the force divided by the area would give you the pressure. All right. Another key aspect of this, though, is that as the particles are moving and they're in the presence of each other, the particles exert no forces on one another. So there's no what we would call intermolecular forces, which we're going to learn later about today. But in an ideal gas, there is no forces exerted between gas molecules on each other. So then taking 2 and 3 together, this is not really an exact postulate of the kinetic molecular theory, but what those two together mean is that any collisions of the gas particles, either with themselves or with the walls of the container, are assumed to be elastic collisions. I always get those two mixed up. Yeah, they're elastic collisions. So basically they bounce right off each other. They don't lose any momentum or speed as they're doing that. So you may have learned in physics class about the difference between elastic and inelastic collisions. Gas particles are assumed to always have elastic collisions with each other, meaning that as they collide with each other, they don't change their total kinetic energy. They just bounce off each other. They can change directions all they want. They bounce off the walls of the container and exert a force on it, but they don't lose any kinetic energy as that happens. And there's no actual force of attraction between the gas molecules, so they're not attracted to each other anyway. They're not repelling each other anyway. They just randomly move about, and if they happen to hit each other, they hit each other. They collide and they change directions. They collide with the walls of the container to make pressure, but there's no real forces between the gas molecules on each other. And then what we'll talk about in more detail a little bit later on in this section is that what's important for determining pressure is the kinetic energy of the gas molecules. So as we said, they have motion associated with them, so they're going to have kinetic energy. Give up on that pen. I keep thinking it's going to work, and it doesn't. All right, so we're back to the one that works. So the average kinetic energy, which is going to be an important parameter for determining pressure, it has a very simple relationship with temperature, so it's just directly proportional to the temperature. We will see the equation later on, although not use it particularly in any problems that we do. But the average kinetic energy of the gas particles is proportional to the temperature. Again, the temperature has to be in absolute units of Kelvin for this to work. And so what this means then is as we increase the temperature of gases, the molecules are going to move faster. So remember, kinetic energy is basically how much energy they have as a result of motion. So you increase the temperature, you increase the kinetic energy, which means you increase the average speed of the gas molecules. So two things then happen. First of all, they're going to have more frequent collisions, both with each other and with the walls of the container. So if they're moving faster, they're going to hit the walls at a more often than they would if they're moving slow. So higher temperature results in more frequent collisions. And those individual collisions then would on average have larger force because the molecules are moving faster. So two things happen when you increase the temperature. You make the collisions more forceful because they're moving faster, but then they also happen more frequently. So both of those, as we'll see in a second here, contribute then to some of the properties of a gas as you change things like this. So that's really a key point that we'll get. This fourth one especially we'll see a lot more details about later on today. So we can now think about gases at the molecular level and sort of rationalize some of the observations of the ideal gas law. So, you might be wondering, what is an ideal gas? An ideal gas is one that obeys those postulates of the kinetic molecular theory. So all those things we just listed on the previous slide, that's what we mean by an ideal gas. It's a gas that has those properties. No gas in the world is actually ideal, but again, under normal conditions, most gases behave at least very close to that. And so we have this ideal gas equation. So the first relationship we talked about was the relationship between pressure and volume. All right, so pressure is equal to nRT times 1 over the volume. So if we rearrange the gas equation, we see that pressure and volume are inversely related to each other. As one goes up, the other one goes down. So let's think about what happens if we decrease the volume of a container. So this is what this picture is showing. We're just going to take this plunger here and force it down to make the volume smaller. So as the volume goes down, we're not changing the temperature in this case, so the average kinetic energy or the average speed of the gas molecules isn't going to change, but by making the container smaller, we're going to have collisions that are more frequent. Remember, the two things we said that can happen when you change something about a gas is that either they move faster and they have collisions that are more forceful, or they just collide more frequently with the walls of the container. So this particular change, decreasing the volume, is going to make the collisions more frequent because you have a smaller space for them to move in, so they're going to hit the walls more often. And if you have more frequent collisions, that's going to cause an increase in pressure, which is what we would predict from Boyle's law. So as we decrease the volume, the pressure will increase because we have more frequent collisions with the walls, and more often that the gas molecules are hitting the walls, the higher the pressure that's going to be observed. Okay? Again, as I said, there's only two things that can really influence pressure. It's the force of the collision and how often it's happening. All right, so if we do pressure and temperature then, that was what we referred to. We didn't actually have a gas law for this, but we can rewrite the ideal gas law and see that pressure is equal to nR over V times temperature. So here we're changing temperature and seeing how pressure responds. So when we increase the temperature of a gas, on average, the particles are going to move faster. All right, we'll see the equations in a little bit, but we should know by now that the increase in temperature means that on average particles move faster, and that means the collisions with the wall of the container are going to both be more frequent and more forceful. So the gas molecules are going to collide with the walls more often, and they're going to have a higher force exerted when they collide with the wall on average. And both of those will then contribute to an increase in pressure. So we would predict from the ideal gas equation that pressure and temperature are directly related. If one goes up, the other one goes up, and this hopefully helps us understand why at a molecular level. If we increase the temperature, the gas molecules move faster, and both of those factors then will contribute to the increase in pressure that we see. All right, another of the simpler gas laws that we learned was Charles's law, which is volume and temperature. This one's maybe a little bit harder to see, but we can predict again from either the Charles' law itself or from the ideal gas equation that volume and temperature are directly related. So if we keep the pressure the same and we have the same number of moles, as we increase the temperature, we expect the volume to increase based on Charles' law. So what happens when we increase the temperature is exactly what we said in the last slide, which is that the collisions become more frequent and more forceful because the molecules are moving faster on average. All right, so this is really almost identical to the argument we made in the last one. So we have collisions that are more frequent and forceful. If we're keeping the pressure the same, as these gas molecules start moving faster, they're going to have to expand the walls of the container to keep that pressure. They're going to be pushing harder initially. So to get to that equilibrium condition where the pressure is constant, you're going to have to expand the volume. So the volume will increase in this situation to make sure that pressure stays constant. All right, so that's really a very similar argument as the last one. This time we're keeping the pressure constant and not the volume constant, though. And then the last one is Avogadro's law. So Avogadro's law deals with volume and number of moles. So if we rewrite the ideal gas equation, volume is equal to RT over pressure over P times number of moles. So again, these are two that are directly proportional to each other. As we add more gas to the sample, we expect the volume to increase. So in this situation, we're not changing the temperature. So we're not expecting the gas molecules to move faster on average, but as we add more gas to the container, they're going to be more crowded in there. The molecules are going to then hit the walls of the container more frequently. So in this case, increasing the number of moles, we have more gas molecules present, which means we're going to have more frequent collisions. All right, in this case, we should recognize that the collisions are not going to be more forceful because we're not changing the temperature of the gas. The only time we can make the collisions more forceful is if we make the gas molecules move faster, and that only happens if we change the temperature. But this time we're putting more gas in there, so there's going to be more frequent collisions. So initially the pressure goes up, but then if we want to keep pressure constant, we have to expand the volume just like we did in the last one to ensure that pressure remains constant. So in this case, again, volume is sort of responding to the initial change in pressure that we would see, and this would cause the piston to expand and volume to increase if we were keeping the opposing pressure constant. All right, so this rationalizes some of the gas laws, and really at its simplest level, there's, just to reiterate what I've been saying over and over again now, there's two things to consider. How forceful are the collisions? In other words, how fast are the gas molecules moving, and how frequent are the collisions with the walls of the container? And the only thing that influences how fast they're moving is the temperature. So unless you're changing the temperature, you're not going to change that. But by changing other parameters, you can change how often the collisions happen, and that will also result in an increase in pressure. All right, so that gives us some things on a bit of a conceptual level. Let's start to look at things a little bit more quantitatively now. So we've talked now about how gas molecules are in constant motion and how we can influence the speed that they move at by increasing the temperature. The reality is that in a sample of a gas, you're not going to just have one molecular speed. There's going to be a distribution. So some are going to be moving slower, some are going to be moving faster. As we'll see, there's an average velocity. That's the one that's actually directly related to temperature. So any sample of gas is going to have a distribution of molecular speeds. So they're not all going to be moving exactly the same speed at any time. There's going to be a distribution. All right. So then what we can plot then to help understand this are some sort of probability distribution. We talked about radial probability distributions for quantum mechanics. This is another type of probability distribution, which is the distribution of molecular speeds with the fraction of molecules on the y-axis. So in other words, what percentage of the molecules have this speed, what percentage of the molecules are moving at a different speed, and plotting that probability as an xy plot. So let's compare three samples of gas here. So if we have a gas at relatively low temperature, this is all, again, semi-quantitative now, we'll have some distribution, as we said. So they're not all going to be moving the same. You're going to have some that are moving slow, some that are moving fast, and then some velocity, which is the most probable. That's where this peak would be. That's the velocity that the most number of gas molecules would have. Okay? And that goes down to the x-axis. That's basically related to the average speed. If you're statistics whiz, there's some differences between the most probable and the average and the root mean square and all those things. We're not going to get into those nitty-gritty details, but essentially this peak here represents the average speed. But there's going to be some that are moving slower and some that are moving faster no matter what. Now, if we take that same sample of gas and we increase the temperature, what's going to happen is we're going to get a broader distribution, and the average is going to shift to higher speeds, as we said. So at a medium temperature, let me label this one first. So the blue one is our low temperature graph. We'll go to an intermediate temperature in green here. So what it's going to look like in green is if we increase the temperature, we're going to have a broader distribution, and the peak is going to shift to the right. Now, ideally, the area under these two curves will be the same because it's the same number of gas molecules. You guys know that my artistic ability is not good enough for that to actually probably be true, but they should be ideally. And this would be what we call our medium temperature, is in green here. So as we increase the temperature, we broaden the distribution, and we move the peak to a higher average value. And then if we go to a higher temperature even than that, we broaden it even further and shift the peak even further, okay? So again, the important thing for us is that the average speed will keep increasing every time we increase the temperature. So this red one here is our high temperature. All right, so that's what happens if we have the same gas and we change the temperature. As we increase the temperature, the average speed increases and the distribution gets broader and broader. And then finally, if we go to, now we're going to look at a few different gases all at the same temperature. So as we'll see a little bit more detail on the next slide, the temperature here is proportional to the average kinetic energy. All right, so what we saw in this first plot was that if you increase the kinetic energy, you also have to increase the velocity if you're keeping the gas the same. So in this first plot here, every time we increase the temperature, the average speed gets higher because temperature is directly related to kinetic energy in this way. Now, if we think about what happens if we have different samples of gas, let's say we have O2 and this distribution looks like this. I'm just going to randomly sort of draw it for O2. So blue is oxygen O2. Now, what we see here is that kinetic energy is 1/2 mv squared. So if we have different gases but they're all at the same temperature, they're all going to have the same average kinetic energy, but the average velocity won't necessarily be the same because the masses could be different. So O2 we know has a molar mass of 32. If we go to helium, which has a smaller molar mass, if we keep the temperature same, the kinetic energy has to be the same, but what has to be then true of the average velocity if it gets smaller, if atom gets smaller? It has to increase, right? Because kinetic energy stays the same at the same temperature. This number gets smaller. That means the average speed has to increase for the kinetic energy to remain constant. So if we go to helium instead, the distribution would look something like this, where again it's a lot like what we saw before with increasing temperature. It's probably even more exaggerated than that, but helium will have a broader distribution and a peak that shifts further to the right, so a higher average speed because it's a lighter gas. So helium has an atomic mass of 4, and then if we go to hydrogen, H2, which has a molar mass of 2, we'd expect an even greater shift. So as we decrease the mass further, the average speed increases even more, and so hydrogen would look something like this, with the distribution shifted even further to the right. So if we have gases at the same temperature, the lighter gases are going to have a higher average speed. So we'll write that as sort of our key takeaway point of this. So at a given temperature, so all at the same temperature here, the lighter gases have higher average speed. All right, and this hopefully helps explain then why when we have the ideal gas equation, it doesn't depend on what type of gas it is. The molar mass of the gas does not factor into the ideal gas equation. Remember, it's just PV equals nRT, nothing about the identity or the mass of the gas. And that's because the pressure term that we most often are interested in is determined by the average kinetic energy. And at a given temperature, the average kinetic energy will always be the same no matter what the gas is. But at a given temperature, the speed will not necessarily be the same because that also depends on the mass. So those are some relationships that come out of this then, at least on a sort of semi-quantitative level. Any questions on those concepts before we move on to the equations? Yes? Well, what's happening is that, and I probably didn't draw it perfectly because I don't draw anything perfectly, but what's happening is that you're basically making the distribution broader, so the area under all these curves should ideally be the same. So if you're going to have the same area under all the curve, but this one is sort of spread out more, then the peak is going to have to be lower than the one that's more narrow. So it's the same number of molecules if you integrate under all these curves. So the peak, but we don't really worry about we're not going to actually calculate what the fraction is in any case. We just want to know that the most probable one, where the peak occurs, that's the one that we can broadly define as our average, and that's what we're going to do in here. So any other questions? That is a good point, though. All right. Yeah, sorry. Well, it's a little bit more complicated than that because these are what are called Boltzmann distributions, where you have basically, again, a whole distribution, and there's a lot of terms that go into that. But in general, as you increase the temperature, you broaden the distribution. So yeah, there would be that relationship in general, but it's more complicated than that, so we're not going to, again, deal with that numerically in any case. Anything else? All right, so let's now see what the equations are. Only really one of these equations are we going to even have to worry about, but some of you like derivations, and I do once in a while too, so I want to go through a few relationships and how we can combine them to get some useful equations here. So as we said, the average kinetic energy, which if you put a bar above something, that's a way of saying average in statistics. The average kinetic energy, as we said, is directly proportional to temperature, and it's a pretty simple relationship. It's 3/2 times R over Avogadro's number. So this is the average kinetic energy for a single gas molecule in a mixture. All right, so we're talking about just one single gas molecule. If you want to say what's the average for an individual molecule, it's this equation here. We're not going to derive this one. We're going to take this as a given. If you take statistical mechanics in the future, which it's not my favorite chemistry class, but it's a good one if you take it in the future. And you'll learn how to derive it. So R is the gas constant. We're going to start seeing in this section that there's a different value of R on the periodic table that we will also use. So the one that we've used previously is R is equal to 0.0821 liter atmospheres per K mole. The value that's more appropriate here is 8.314, which is joules. So anytime we're dealing with speed, energy, stuff like that, we use the other value of R. Like I said, we're not actually going to use these equations, so that's not a big deal for us. And then Na here is Avogadro's number. So we're talking about an individual gas molecule's average speed, so we have to divide by Avogadro's number because R is per mole of gas. All right, so that's that first equation there. T, of course, is temperature, as it always is. All right, so that's average kinetic energy. Now we know that there's another relationship for average kinetic energy, which is that it's equal to 1/2 mv squared, as we saw in the last slide. So m is the mass of the gas atom or molecule. I don't remember if your book uses U or V, but I'm going to use V because that's the more conventional one, I think. At least the one that you've probably seen before for velocity. So here we have the standard equation for kinetic energy, where m is mass of the particle that we're considering. And then this average V squared is the average of the squares of the molecular speed. So we take basically we square all of the molecular speeds that are present in the distribution, and then we take the average of them. That's what this little V square of the bar over it is. All right, so if we combine these two equations, so basically we set these two equal to each other because they're both equivalent to kinetic energy, we can then get another equation that says that 1/2 mv squared is equal to 3/2 times R over Avogadro's number times temperature. So that's just combining the two equations that are both equal to kinetic energy. And then we can rearrange this a little bit, and we see that if we move Avogadro's number over to the left side, 1/2 times Avogadro's number times the mass of the individual molecule times V squared is equal to 3/2 RT. And remembering our definition of the mole, if we have Avogadro's number and we multiply that by the mass of an individual molecule, what do we get? So what's the equivalent quantity for that? Avogadro's number times the mass of an individual molecule. Sorry? So this would give us a number of molecules, and if we multiply that by the mass of an individual molecule, what is that mass equivalent to? Yes, and specifically it's a mass of 1 mole of those molecules. So we would call this product the molar mass, as we always do. All right, so we rewrite this then, and we solve for V squared. So we're going to replace this with molar mass, solve for V squared, and we get that V squared is equal to 3RT over Avogadro's number times the mass, which is equal to 3RT over molar mass. All right. And then finally, when we take the square root of the average of the squares, we get what's called VRMS, which is root mean square. Again, we're not going to worry about the precise statistical definitions of that, but VRMS is just the square root of that, 3RT over molar mass. So it depends on the temperature, it depends on the molar mass, as we said, to determine what the average speed is. We're going to, for our intents and purposes, we're going to consider VRMS, root mean square, to be just the average velocity. It's not exactly equal to the average, but it's close, and for our purposes, for our sort of low-level statistics analysis we need to do on this, that's what we're going to say. So that's the equation that comes out of this. Now, we're not actually going to use this equation, but it does help us confirm some of the concepts that we learned, which is that temperature is, the average speed does depend on the temperature. It's directly related by the square root, and the average speed is then also inversely related to the molar mass. So as you increase the molar mass, you decrease the speed, and that's sort of what we showed on those graphs in the last slide. Now, there is a form of this equation that we are going to use a lot, but we're going to get there here in a second. But first, just to give you an idea, what is the RMS speed for a sample of argon at 17 Celsius? 17 Celsius is about, 63 Fahrenheit, I think, so relatively mild temperature. And We just want to know what's the average speed for argon if we have it at that temperature. So as we just saw, this equation, you're not going to do any homework questions where you use it, so, but I just want to show you it in practice so you can get an idea for what the numbers come out to if you're curious. So we use this equation for VRMS, and we just start plugging things in that we know. So 3RT, so 3, and then R that we're going to use here. You'll notice on our periodic table that we have two values of R, just two different units. It's the same constant but two different units. And one of them is 8.314 joules per k mole. So anytime we're dealing, again, with energy, speed, stuff like that, we're going to use this value of R. So we use 8.314 for R. And then the temperature has to be in Kelvin, so 17 Celsius is equal to 290 Kelvin. We add 273 to that. And then we divide by the molar mass. The one tricky part about this equation, and one reason why, again, we're not going to have you actually use it for homework problems, is that because we're dealing with SI units here, which is joules, we can't use grams per mole for molar mass because grams is not the SI unit for mass. We have to use kilograms. So the molar mass in kilograms per mole for argon, the mass that we get from the periodic table is 39.95 for argon, which is grams per mole. So you have to convert that to kilograms per mole by dividing by 1,000. All right, so that's one tricky part of this equation that's not obvious from just looking at it, but the mass needs to be in kilograms for that value of R to work. So it's 0.03995. All right, so it's 426 meters per second. That's actually pretty fast. I know we don't use speeds of meters per second in our everyday life. I'm trying to remember. I think it's about, I could have this wrong, but it's not going to be too far off. I think it's about 2 miles per hour per meter per second. So, 426 meters per second is like 800 miles an hour on average. So gas molecules are moving very fast, as it turns out. So that's what this tells us. Like I said, we're not going to use this equation and you're not going to be responsible for using it, but it does show us that these are moving fast, and this is how you would calculate the actual numerical value for the average speed if we were interested in that. All right, but what we're going to actually do with this equation is talk about it more in a relative sense and in the context of two other sort of processes for gases. So this again just tells you how fast the molecules are moving, and then two processes that are related to how fast they're moving are effusion and diffusion. So these are two different concepts. We should be familiar at least with the definitions of them, although the equations that we use for both of these are the same. And both of these, as we'll see, are related to how fast the gas is moving. So effusion is the escape of a gas through a tiny hole. So you can think of this as a leak rate, is effusion. All right, so then, what we'll be able to do then after we go through this section is, let's say we had, two balloons. One was filled with nitrogen and one was filled with hydrogen. And we were skillful enough to poke holes in those balloons without popping them, which is, if you ever tried, difficult to do, but not impossible. So then we have two balloons with holes in them, one with hydrogen, one with nitrogen. Which one's going to leak out faster? And that's what effusion refers to, is how fast something leaks. And we can use some equations we're going to see here in a second to predict that, especially for two gases relative to each other. And then diffusion is another process that involves movement of gas molecules. And this time it's the movement of a gas through another gas. So we talked about diffusion a little bit, although not using this terminology in the beginning. So as I said, if I took a really small sample of a terribly smelly gas like dimethyl sulfide, which is what's used to give the odor natural gas, if I release a little bit of that at the front of the room, eventually the people in the back are going to smell it, and that's because the gas molecules diffuse through the air in the room and spread out in all directions. So if we had two different foul-smelling gases at the front of the room, and we were to release them at the same time, which one would diffuse faster, get to the room, back to the room first? That's what diffusion refers to. And again, the same equation that we're going to derive also refers to the rate of diffusion. So we're going to see the equation then is that both of these effusion and diffusion are proportional to the root mean square velocity. Now they're not exactly equal to it because again it depends on a lot of other factors like how big is the hole that it's leaking through, what's the pressure of the gas that's diffusing through, all kinds of things would determine these absolute values, but the relative value is proportional to VRMS, which we just derived in the last slide here, the equations for that. So then what we're going to do for effusion and diffusion is typically compare two gases to each other, not actually calculating an absolute rate, but actually just comparing two and looking at the ratio of the rates. So if we have two gases A and B, the rate of that one effuses or diffuses, this rate equation refers to both effusion or diffusion equivalently. And we said before that these are proportional to the root mean square velocity, so we can take the root mean square velocity for both of them and just write those in as 3RT over molar mass. So we always have to compare two gases at the same temperature so that we have the same T, different molar masses though for the two gases, so they're going to have different VRMSs as long as they don't have the same molar mass. So if we're comparing two gases with two different molar masses, what we see then is that the 3RT is a constant for both of them. We have to compare them at the same temperature. R is a constant, 3 is just a number, so it's a constant. So then this simplifies to the molar mass of B over the molar mass of A. So when we're talking about the rate of effusion or diffusion, there's an inverse square root relationship to the molar masses. So the rate of A over the rate of B is equal to the square root of molar mass of B over molar mass of A. All right, so that's one form of the equation that we'll use, which is just dealing with the rates of effusion or diffusion as they compare to each other. Again, not getting absolute rates, but comparative rates for two different gases. Other forms of the equations that we will sometimes use, so if we're talking about diffusion, we can think about how far does a gas diffuse relative to another. So it's not necessarily thinking about the rate in this case, but the distance that it diffuses in a period of time. So remember that these are all related to root mean square speed. Speed, the basic definition, is distance over time. So if we have two gases and one is moving faster, the gas is moving faster, is it going to move farther or not as far during the same period of time? Or in other words, think about it in terms of cars. If you're driving your car 60 miles an hour versus 30 miles an hour, if you drive for an hour, which one goes farther? The faster one, right? So the faster gas is going to travel further in a given period of time. And so the equation then for the distance traveled is exactly the same because distance and speed are directly related to each other. So the distance that a gas travels in a period of time is proportional to how fast it's traveling. And so in terms of distance, the equation looks exactly the same. So the distance that one gas travels relative to another is again equal to the inverse square root of the molar masses. So same exact equation as before. All right, and the only reason I'm introducing these is not because they're all totally different concepts or different equations, but just to give you a flavor for how we can introduce this information. So we can talk about it in terms of the rate that they're effusing or diffusing, which is sort of the standard form of the equation. We can talk about it in terms of how far something diffuses in a period of time, which would be then this relationship. The one that gets a little bit different, though, is in terms of period of time. So if we're talking about, let's say, a leak rate for two balloons, we want to know which balloon leaks faster than the other, which one takes a shorter amount of time or a longer amount of time for the gas to leak out. From this equation here, remember that speed equals distance over time, so speed is inversely proportional to the amount of time that it takes. And again, thinking about it in terms of how cars drive on the road, if you're commuting to work and the traffic is good, and you can drive 60 miles an hour the whole way, you'll get here in some period of time. If the next day the traffic is terrible and you're stuck at like 30 miles an hour, it's going to take you a longer period of time. So the faster it's moving, the longer the shorter the period of time, the slower it's moving, the longer the period of time. So they're inversely related to each other. And so what that means is if we're comparing the time that it takes two gases to effuse or diffuse, this time it's going to be directly related to the molar masses. So we have to flip one side of the equation, and so in this case it's going to be directly related to molar mass, still under the square root. but now not flipped on the other side of the equation. And this, so sometimes it's hard to keep these two forms of the equation straight, but think about it conceptually, right? We know now that the heavier the gas is, the slower it's moving at a given temperature. So if we're talking about how far something is going to be moving, that's going to be inversely related to the molar mass, because the heavier gas is going to be moving slower, so it's going to move a less distance. But if we're talking about how long it takes something to go, the heavier gas is going to be moving slower, so it's going to take a longer period of time. So time and molar mass are directly related there. So it's a common mistake people make to use the wrong form of these equations. So just make sure we're familiar with that there are two forms of the equation and when to use them. We'll give some examples of that here as we go through. All right, so any questions on the equation before we start using them? All right, so let's just see a few representative examples of problem setups. So let's say we have a sample of hydrogen and helium. Again, we could think about it as the sort of poking a hole in a balloon experiment. But we want to know which gas effuses faster and by how much. So here we're just talking about relative rates of effusion for two, which is sort of the standard way of thinking about it. So we have hydrogen and helium are the two gases we're considering here. And we didn't really specify very particularly how we're going to set this up. But let's just take the rate of the effusion of hydrogen over helium. We could do it the other way too. We get to the same conclusion eventually. Then remember, if we're talking about rates of effusion, it's going to be inversely related to the square root of the molar masses. So it's going to be, if we have rate of hydrogen over rate of helium, it's going to be molar mass of helium over molar mass of hydrogen on the other side of the equation. Okay? And so for this problem, we just have to put in the molar masses, and then we're all done. So it's going to be molar mass of helium is 4 grams per mole. This time it doesn't matter what the units are because they're going to divide out. So when we calculated speeds, we had to use kilograms per mole, but if we're doing a ratio of 2, we can use the standard unit, which is grams per mole. Hydrogen H2 is 2.02 grams per mole. Those were given to you directly. We do have to remember that hydrogen is H2. If we didn't tell you what the molar mass was, it should be for H2. And those are the two gases, and then what we get is square root of 1.98, which is about 1.41. So that means the rate of H2, for its rate of effusion for H2 divided by the rate of effusion for helium is equal to 1.41. Or another way to say this is that H2 effuses 1.41 times faster. All right, because again, the ratio is greater than 1, so that means the rate of effusion for hydrogen is faster than helium, which makes sense because hydrogen has a smaller molar mass, so it should be moving faster, should be effusing faster as well. So all this checks out. All right, questions on that? Yeah. Yes. Correct. So the reason is that here they divide out. So it's grams per mole in the numerator, grams per mole in the denominator. So those just cancel out. So whatever units you put there will work. For the other one, because we're using R here, it's not obvious why this is, but R is in joules, and joules is like kilograms, meters per second squared, whatever the physics definition is. So joules is a compound unit that includes kilograms in it. So in order for this to divide out properly, this has to be in kilograms here. But if you're doing, anytime you're doing a ratio, like as we saw for a lot of the ideal gas equations too, if it's a ratio of two parameters, temperature is the one that's non-negotiable, has to be Kelvin, but for other parameters, as long as what's in the numerator and the denominator have the same units, they'll cancel out, and you can choose whatever's convenient. And that's what we did here. All right. Other questions? Okay, so let's then move on to another one. This one's in terms of time. So it's if it takes 1.25 minutes for 0.01 moles of helium to effuse, how long will it take the same amount of ethane to effuse? So we should recognize we gave you here the amount of substance, but in the effusion-diffusion equation, the only one that we need to know, the amount of substance, moles or whatever, doesn't even show up. So that number is just a throwaway. It's just telling us that we're comparing the same amount of the two gases, but we don't actually have to use the 0.01 for anything in this problem. Because remember, there's only one equation we have to worry about, and then a slight variation on it as well for effusion and diffusion. So here we're talking about effusion, so we're going to do the ratio of the times. We know the time that it takes for helium to fuse is 1.25 minutes, so we can set up the equation either way. If we put C2H6 on top, which is the other gas, ethane, and we put helium on the bottom, we could again have inverted it, we'll get the same answer, so it doesn't matter how you set this up. The algebra will be a little bit easier this way, so that's why I'm doing it this way. But if you did it the other way, it's fine. It'll work out. All right. So then that's going to be related to. Now remember, we're talking about time here. So the gas that's heavier should take a longer amount of time to effuse or diffuse because it's moving slower. So ethane is the heavier gas, so it's going to take a longer period of time. So that means time is directly related to molar mass. So it's going to be the molar mass of C2H6 over the molar mass of helium. So remember, when we're dealing with units of time, that's the one time when we have to flip one side of the equation and make the two directly related. C2H6 on top on both sides, same with helium on the bottom on both sides. All right, so then we can either start plugging in numbers or we can work it out algebraically. So we're looking for the time that it takes ethane C2H6 to effuse. So we're going to solve for that. That's going to be equal to the square root of the molar mass ratios. Multiplied by the time that it takes for helium to effuse, which we gave you in the problem. All right, so the molar mass for ethane is given as 30.08. The molar mass for helium is 4. And the time that it took for helium was 1.25 minutes. All right, so we take the square root of the molar mass ratio, multiply by the original time, which is 1.25, and we get 3.43 minutes is what I got numerically. So it should take longer because it's a heavier gas. That makes sense to us. And it's roughly 3 times longer, a little bit less than 3 times longer once we do the square root. So get used to doing square roots on your calculator, because I know occasionally there's some different syntaxes for the different types of calculator. I think this is the first time where we had to do square roots, so make sure you're familiar with that so it doesn't trip you up on the test. So that's another variation where we're solving for one of the effusion rates, or in this case the diffusion time. And then the last variation is to solve for molar mass, which is what we're going to do here. So we would have 7.23 milliliters of an unknown gas effuses in the same amount of time as 13.8 milliliters of argon under the same conditions. What is the molar mass of the unknown gas? So in the same period of time, less volume of the unknown gas effuses, which means that it should be a heavier gas. So again, think about things conceptually a little bit first before we start plugging in numbers. So this is a gas that should be heavier than argon because in the same period of time, more argon leaked out than the unknown. So that means the unknown gas has to have a higher molar mass, be moving slower for this to be true. So if we start writing out the equations, then the rate that argon effuses, or the amount of argon that effuses as it's sort of stated here, over the rate of our unknown is equal to the square root ratio that's going to be inverted now. So it's going to be molar mass of the unknown gas divided by the molar mass of argon. All right, so again, here we're talking about how fast or how much leaks out in a period of time, which is related to the rate. So we're going to solve for the molar mass. And remember, if we have two things under a square root, we can also write that as the ratio of the square roots individually. And so we're going to solve for that unknown molar mass, because we have the ratio of the rates is going to be given by how much of each gas effuses in that period of time. We have the molar mass of argon, so we just have one unknown, which is the molar mass of our unknown. Because the algebra is a little bit different here, I'll go through it in a little bit more detail than I normally would. So we're going to cross multiply to get molar mass of argon onto this side. And then we're going to isolate molar mass of our unknown. So the square root of our unknown molar mass, if we just rearrange now, is equal to the ratio of the rates times the square root of the molar mass of argon. All right. And remember, we haven't done algebra with square roots yet, so just to refresh yourselves if you haven't done algebra in a while, at least this type of algebra, we're going to square both sides to get rid of the square roots. So we square that side, we square everything on the other side, the whole thing, not just part of it. And so then the rewritten equation would be that the molar mass of X, so once we square that, we get rid of it, is equal to the ratio of the rates squared. You could also do this numerically, as I said, so if you prefer, just plugging numbers in, go ahead and do that. That's not a problem, but that's how we get it when we, so we're going to square that ratio and multiply by the molar mass. All right, so we said that the ratio of the rates is equal or equivalent to how much leaks out in a period of time. So 13.8 milliliters for argon leaks out in that period of time over 7.23 milliliters of the unknown. We square the ratio and we multiply by the molar mass of argon, which is 39.95 grams per mole. Again, in this problem, the units you can use the standard ones. So those divide out, we get an answer in grams per mole, which comes out to 146. All right, so we determined at the beginning that it should be a larger molar mass because less of it is diffusing, and this number is larger than the molar mass of argon, so at least it makes sense from that respect. So the algebra is a little bit different on this problem, and in some of these that involve square roots, so just make sure you're not tripped up by that as you do these types of problems. All right, any questions on effusion or diffusion? I think, all right, the last one we're going to do that's related to this then is a common sort of chem lab experiment. I think you guys do this in the lab, although this is one that I've heard doesn't usually work very well. I don't know if you found the same thing, but I've never actually done it myself, so I can't comment on that specifically. But we're going to give you some background on a common diffusion experiment to sort of demonstrate the laws of effusion and diffusion, and the math that goes behind then calculating these things. So in this particular example, what you're doing is you're taking ammonia, which is a gas, and HCl is a gas. Typically, you put aqueous solutions on cotton balls on both sides, and the gas sort of, diffuses off of the surface and comes together. So you're having gas diffusing in both directions. NH3 down the tube that way, HCl down the tube that way, and they're going to meet somewhere in the middle. And what they form is a solid, and that's what this little white solid is here that's shown in this tube in the blow-up view. That's NH4Cl, so it forms an ionic compound. This is just an acid-base reaction, although it's not occurring in aqueous solution, it's occurring in the gas phase. And so the acid and the base react, and they make solid ammonium chloride. All right, so the two gases effuse, and you make solid ammonium chloride in the middle, and basically you can easily measure where the two gases meet because you're going to get this opaque white ring where the two gases actually met each other in the middle. All right, I've heard this is tricky to work out exactly this way, but that's, in theory, what's supposed to happen. So the chemical equation is, again, gas phase ammonia plus HCl is a gas. There's an acid-base reaction, so the H plus gets transferred from the HCl to the NH3, and you get ammonium chloride, NH4Cl as a solid. All right, so we're going to start at opposite ends of the tube. The two reactants start at opposite ends. The NH3 gas and the HCl gas diffuse until they meet and react. And once they do meet, that's when they can actually react with each other to form the NH4 solid, NH4 chloride solid, ammonium chloride. All right, so that's sort of the description of the experiment. And now that we know Graham's law of effusion, diffusion, which in this case is really diffusion that we're talking about, we can use that to predict where exactly the two reactants will meet. So how far from one end, how far will the ammonia travel, how far will the HCl travel, and where exactly in this length of tubing will they meet up with each other. So let's see how that works numerically then. So if we take the same two gases, HCl and ammonia, and we're going to release them from the opposite end of a tube that is 30 centimeters long, so that's the total distance that they travel, and we want to know how far does the ammonia travel before reacting with the HCl. All right, so again, the picture is this in a very crude sense. We have a tube that's 30 centimeters long, so that's our total distance. We're going to start with ammonia on one end, HCl on the other, and they're going to travel some distance and meet in the middle. Maybe not exactly the middle, but somewhere inside of the distance of the two. And that's where they're going to meet. So what we're looking for then is this distance here, the distance that the NH3 travels before meeting up with the HCl that's coming in from the other direction. So the first thing we can do is we can write sort of the Graham's law of effusion equation and say that the ratio of the distances, the distance that HCl travels over ammonia. So remember, the distance that they travel is proportional to how fast they're traveling, so that's going to be the standard form of the equation that has an inverse square root relationship. So the ratio of the distances is going to be the inverse related to the ratios of the molar masses. So we have to have them inverse related. Again, we could do it the other way too with NH3 on top, and then we have to flip the other side of the equation as well. So we put the molar masses in. The molar mass of ammonia is 17.03. The molar mass of HCl is 36.46. So we can use this ratio to figure out the ratio of the distances that will be traveled. And so that comes out numerically to 0.683. So the distance that HCl travels over the distance of NH3 is 0.683, or alternatively, the distance that HCl travels is equal to 0.683 times the distance that ammonia travels. All right, so there's that relationship between the two distances. If you did it the other way, you would just get the reciprocal of that number. No problem there. It would still work out at the end. So that gives us the relative distances, but what we want to know in this case is the absolute distance that it travels. So the other piece of this is to recognize that the sum of the two distances has to be equal to the total length of the tube, which is 30 centimeters. All right, because again, that's our entire distance, 30 centimeters. They're going to meet in the middle, and the total that they travel from each side is going to be equal to that. So that's the second equation, and we're going to replace the distance that HCl travels with this relative distance here for NH3, because we're solving for this distance for NH3. So we get 0.683 times the distance that ammonia travels, that's replacing this variable here, plus the distance that ammonia travels equals 30 centimeters. And now it becomes a simple linear equation where the distance that ammonia travels is 17.8 centimeters, which then means that the HCl would have traveled about 12.2. The remaining 30 centimeters would be how far HCl travels. You should again make sure that your answer makes sense. So HCl is a larger molar mass than ammonia. So the one that's larger is going to move slower. It's not going to travel as far. And so that means ammonia, which has the smaller molar mass, should travel more than half of the distance, which what we got here is 17.8. Okay? Any questions on this type of problem or this concept? All right. So the very last thing we're going to talk about with gases then is real gases, ones that deviate from ideal gas behavior. So everything we've done up until now, the ideal gas equation, which has that in the name, the kinetic molecular theory of gas, which explains that at an atomic level, everything deals with what we call ideal gases. And those are the ones, as we said, that we assume they have no volume. The gas molecules themselves have no volume. We assume that they're elastic collisions, constant random motion, all these things that we talked about on the very beginning of today's lecture. But in reality, these types of behaviors are, for real gases, are not going to always be observed. So if we want to talk about the behavior of real gases, we can start with the ideal gas equation, which is PV equals nRT. And for an ideal gas, then, if we take the ratio of PV over nRT, so if we divide both sides by nRT, that ratio should always be equal to 1 for an ideal gas. Because for an ideal gas, PV and nRT are equal to each other, so if you divide the two, you get ideally 1. So this is what it would look like. For an ideal gas, if we take the ratio of PV divided by nRT, as we increase the pressure, we should get just a constant straight line that equals 1, because no matter what, for an ideal gas, that ratio should be 1. Now let's see what actually happens for real gases. So if we start for hydrogen, we get sort of as we increase the pressure, we're going to slowly get a deviation from that. So this is and again, these are all qualitative graphs, so don't worry about the quantitative differences, but that's what it would look like for hydrogen. That's kind of not the most common behavior. In most cases for real gases, what you see, if we do it for, let's say, nitrogen, is that you're going to initially get a dip. You're going to get a negative deviation initially where the ratio of PV over nRT is less than 1, and then it's going to start increasing at higher and higher pressures. So most real gases, the ratio of PV over nRT is not exactly equal to 1. It's going to deviate sometimes below that, and then at other pressures above that as you go to higher and higher pressures. If we go to another gas, CH4, methane, you'll see larger deviations than you get for nitrogen. And then if we go to CO2, deviation is larger still. Now, stuff that we'll talk about in the next chapter will help us sort of predict which gases are likely to deviate more than others, so we're not going to deal with that today. But the point of this is that all gases are going to have some deviation from ideal gas behavior, and it's most pronounced when you go to really high pressures. At relatively low pressures, I didn't maybe draw this as perfectly as I could have, but at low pressures the deviations are very small, and for most gases the ratio of PV over nRT will be very close to 1 if you're at the sort of reasonable pressures that we normally work with. But as you start going to hundreds and hundreds or even thousands of atmospheres of pressure, you're going to start seeing deviations where this ratio is not exactly equal to 1, and that's sort of going to be true for any real gas that exists in our world today. So no gas is perfectly ideal. There's always going to be some deviation. The deviations are most pronounced at high pressures. So if we want to think about then, one of the concepts that we want you to understand, we're not going to do a lot of real in-depth treatment of real gas behavior. It's a bit complex for this course. But one of the things we do expect you to understand is when do real gases behave most like the ideal gases? So when is the ideal gas actually going to be followed pretty closely? So one set of conditions that's necessary for these gases to behave most ideally is relatively low pressure. So anytime the gas particles are far apart from each other, they're going to behave pretty ideally. So that's really for two reasons. The one is that it minimizes the interaction. So we said that one of the postulates, one of the tenets of the kinetic molecular theory of gases, which governs ideal gas behavior, is that there's no interactions between gas molecules. So that's one thing that's not actually true, but if you keep the gas molecules really far away from each other, they're not going to interact very much because they barely ever see each other. There's a lot of space between them. So that's one thing, is that if you have a low pressure or a very large volume, you spread the gas molecules out from each other so they don't interact with each other, and they're going to then better follow the ideal gas behavior. The other thing that's true is that if you have low pressure, we know that the volume of the particles will be very small compared to the volume of the container. So if the pressure is low, or alternatively the volume is very large, which is really saying the same thing, this tenet of the ideal gas law will be more true in those situations as well. Because we said that another key component of ideal gas behavior is that they have zero volume for the atoms or molecules, which is not really true. But if you have a very large container volume, the volume of the particles is very small compared to that, and that assumption is at least close to being correct. So one situation where so if you're talking about pressure and volume, real gases are going to behave most like ideal gases when the pressure is low and the volume is large. Those are the situations where the molecules are spread as far apart from each other, they're not interacting at all. Now the other situation is at high temperature. So if we talk about the temperature side of things, if the temperature is higher, you're going to have more following of the ideal gas behavior. So this is because at high temperature the gas particles are moving very fast. And if they're moving faster and faster, they're going to spend less time interacting with each other. All right, because for ideal gases, we assume that the gas molecules don't interact with each other at all, that they're just zooming past each other. So the faster they're moving, the more they're going to follow that type of behavior. If they start slowing down, they're going to start colliding with each other more often, they're going to start interacting with each other more, and they're going to deviate from that typical gas behavior. The other thing that we'll learn in Chapter 9 is that if you take a typical substance and you cool it down enough, the gas is going to turn into a liquid. So basically, the lower the temperature goes, it's going to start behaving more and more like a liquid, less and less like a gas. Whereas if you have the temperature really high, it's going to behave more typically like a gas. Yes? Yeah, for our purposes now, we'll just sort of associate those with collisions. We're going to talk at the very beginning of chapter 9, which is coming up here in a second, about what the actual types of interactions are between molecules. And those are called intermolecular forces. So this is another one of those topics, like a lot of the things we've seen, that's going to make the most sense once we've covered all of 7, 8, and 9 that are all related to each other. So we'll talk in more detail about what that means. But for our purposes, it just means collisions, and we're going to see in more detail how that refers to forces of attraction between gas molecules, which are more prominent when they're moving slower and able to collide more often. So that's what we mean by that. So any questions then? Yeah, sorry, you have one more. Go ahead. So they collide more frequently, but they're not in contact for as long, basically. So these types of interactions that cause deviations from ideal gas behavior, the more period of time that the gas molecules spend next to each other, they're going to have those forces of attraction be stronger and more prominent. So that will again make more sense as we go to chapter 9. But for now, just know that the ideal gas behavior occurs when you have low pressure, high volume, high temperature. That's when you're going to get the most ideal behavior for any gas. All right, anything else? So there is an equation then that deals with real gases, although it's another one of these equations that we're going to introduce, want you to know the concept of, but not actually do calculations with. So again, you won't see any homework questions where you have to use this equation, but it is helpful to know to help us think about real gases and to understand at least at a conceptual level. So what we're doing with the van der Waals equation, which is what this is called, is we're modifying the ideal gas equation to account for the fact that no gas actually behaves as an ideal gas. So what you do is you take the pressure term in the ideal gas equation and you modify it with n squared times A over V squared, where n and V still have the same definition, number of moles and volume. A is a van der Waals parameter that we're going to define here in a second. And then you adjust the volume term with an n times B. So again, n is number of moles, B is going to be another parameter for that gas. And those are going to be equal to nRT. So this is just a modified, more complex form of the ideal gas equation. This is a purely empirical equation. So this isn't derived from any sort of physical principles. It's just that, people who really, good at math and chemistry together, I suppose, they just took all the behavior of real gases and they just parameterized the function. They just figured out, how many parameters do we need to make this fit the actual behavior better? What is the numerical value of these parameters that works best? And it's just purely an empirical approach to make it fit better, but it doesn't have any real basis in physical reality. Now, there is some basis, though, for what these A and B terms refer to, okay? So A and B are called the van der Waals parameters, and so what A adjusts for is those interparticle interactions that occur in real gases, which, as a teaser, once again, we're going to cover in Chapter 9 what exactly those are. But for now, this is a term that sort of accounts for that behavior. All right, so what this A term here is doing, or the whole term that it's associated with really, is it's adjusting the pressure to account for the fact that there actually is going to be some force of attraction between gas molecules that exist in real life. So it's adjusting the pressure upwards to account for the fact that there's going to be some attraction between the gas molecules that's going to prevent them from colliding with the walls as often as they normally would if they weren't interacting with each other. So A adjusts for those interactions, and then B is a term that accounts for the fact that the gas molecules themselves do not actually have zero volume. All right, because if we were to take, every atom and molecule has some size associated with it. So if we were to take a gas molecule, a sample of gas and compress it down and put the particles really close to each other, the volume of those gas molecules in atoms is going to be significant. So B adjusts the volume term. So adjust the volume term to account for particle volume. Again, the fact that the volume of atoms and molecules is not actually zero, which the ideal gas equation assumes. Another way to think about this B term, which again shows up there with the volume, is that the ideal gas equation only works if we assume that all of the volume is empty space. And so basically this B term here subtracts out the volume of the actual gas molecules, so that we're only then accounting for the volume of the empty space with this whole term there. So that's another way to think about it. Again, we don't have to really use this equation. We just want to, at least at a basic level, understand it. And it just adjusts the ideal gas equation to account for the real behavior of gases. And so then taken together, then A and B, as we said, are called the van der Waals parameters. So these are the sort of more essential things you want to know. They're called van der Waals parameters. These are experimentally determined, or as I said, empirically determined quantities. They're not derived from any sort of physical principle or any sort of other equation. They're just experimentally determined numerical parameters, and they're unique for each gas. There's not one value of A or one value of B that you would know that could adjust the ideal gas equation. It depends on what gas you're talking about. So basically, the stronger the interactions between the gas molecules, the larger the value of A is going to be. And the larger the size of the gas molecules, the larger the value of B is going to be. And so we can learn now in Chapter 9 coming up how to predict which gases are going to have stronger interactions, and that would then relate back to this van der Waals equation in terms of term A here. Basically, the point is that A and B are unique for each gas, so depending on which gas you're trying to use this equation for, you'd have to use different values of A and B, and those are all, again, empirically determined and parameterized appropriately. All right, so we're going to move on now to... We're going to transition into Chapter 9. We're not going to really do a lot with this today, but we're just going to sort of do the transition. So we've now been talking about the transition from ideal gases to real gases, and how one of the key things that is different is that in ideal gas theory or kinetic molecular theory, we assume that the gases don't interact with each other at all, but in real gases, liquids, and solids, that's not going to be the case. So the key assumption from the kinetic molecular theory was that gas particles do not interact with each other. So that's what we covered at the beginning today, is one of the assumptions of KMT, or kinetic molecular theory. But then when we're talking about real gases, so gases that are not ideal, liquids and solids, that's not actually the case. So we just discussed that in the context of the van der Waals equation, that real gas molecules do have some interactions with each other. And then in liquids and solids, those interactions are even more pronounced. So you might be wondering, why are some substances gases? Why do they just fly around everywhere as gases, whereas other ones, stay as a liquid? Why is, if we're at room temperature, why is oxygen a gas? Why is water a liquid? And that's because when you have liquids, you have stronger forces of attraction between the molecules that hold them together in the liquid phase and stop the molecules from just flying all over the place like you do in a gas. So those interactions are very important, especially in the condensed phases where we're talking about liquids and gases. So in these condensed phases, or in real gases, you have the atoms or molecules are actually in constant contact with each other. And that's especially true in condensed phases where they are really, packed together very, very tightly. And there's interacting forces at play that sort of hold them into those condensed phases. So these interacting forces hold the molecules together into these condensed phases, liquids and gases especially. All right, so as we get into this, then we're going to talk about then these interacting forces, and we're going to see in a lot more detail next time. But just sort of the basic definitions to start. These are called intermolecular forces. These forces of attraction between molecules are called intermolecular forces. So if you've ever taken Latin in high school like I did, which was not my favorite class, but okay. Anyway, inter means between. So anytime you see inter as a prefix, that means between, involving two different things. So these intermolecular forces are forces of attraction between two molecules, or two different atoms if you're talking about an atomic element. But whatever, it's two different particles that make up that substance, and this force of attraction between two different ones. So a couple points of confusion to clear up at first. So intermolecular forces have nothing to do with chemical bonds. Okay, this is a totally separate context. So a very common mistake that people make is We're going to learn later on how to sort of rank or quantify, or at least in a relative sense, quantify the strength of an intermolecular force. It has nothing to do with how strong the covalent bond is between the two atoms or whatever type of bond it is between the two atoms. Those are two separate concepts. Intermolecular forces are much weaker than chemical bonds. So if you have a sample of liquid water, the bond energy between the oxygen and the water, the hydrogen and the oxygen in water, that's holding those molecules together, the H2O molecule, that's each individual OH bond, I think, is something on the order of like 400 kilojoules per mole. There's going to be much weaker interactions between the individual molecules. Those are the intermolecular forces. Those are going to be, probably about a factor of at least 10 less than that. So they're much weaker forces that we're talking about, and they exist between two different molecules, not within a single molecule. So they have nothing to do with the individual bonds in a molecule, and related to that, they have nothing to do with covalent bond strength. All right? Covalent bonds are what we refer to as intramolecular forces. Here we're talking about intermolecular forces. So we're going to, again, define intermolecular forces in more detail next time, but we want to be familiar at the very start that these are not referring to covalent bonds or any type of chemical bond. These are forces between separate molecules that are held together individually by the bonds. We're talking about the forces that are between separate molecules. So let's make sure we don't get those confused at the outset. And then the last thing we're going to cover today is just a quick review of phase changes, because a lot of what we're going to talk about in this chapter is how these intermolecular forces influence what phase of matter something exists as, whether it's solid, liquid, or gas, and how it's able to interconvert between those phases. All right? So we talked about gases in Chapter 8. In Chapter 9, we're going to introduce liquids and solids. So the process of going from a liquid to gas is referred to as what? This could be a review for some of you. So it's called either vaporization or boiling. We'll see sort of the precise definition later. And then the opposite process, which is going from, I should probably call that vaporization. That's a better way to say it for now. All right, so I changed my mind. I'll call this vaporization. And then the opposite process, which is going from gas to liquid, is called, anybody know? Condensation. So when you see condensation on your windshield on a humid morning, that's basically water vapor going from the vapor phase, from the gas phase to the liquid phase on the surface of the glass. So condensation is the opposite process. What we refer to as the boiling point, which we're going to define more precisely a bit later on, is this is the temperature at which the liquid and the gas spontaneously interconvert. So I'll put vaporization / boiling. I'll change my mind once again. They have different contexts, but they kind of mean the same thing in this regard. So the temperature at which this happens naturally or spontaneously is called the boiling point. And we'll get a more precise definition later on. And then the other phase of matter, if we convert between the condensed phases, liquid and solid, liquid to solid is called freezing. And the opposite process, solid to liquid, is called melting. All right, those should hopefully be familiar to us as well. And then this temperature at which this occurs is called either the freezing or the melting point. These are used interchangeably. We don't really call it the condensation point, but I guess it could be in theory. But freezing and melting point are used both interchangeably, and this is the temperature at which these two phases interconvert. I always wonder why we say it's freezing outside, not why we don't say it's melting outside, but that's a conversation for another day. But the temperature at which this happens is called the freezing or the melting point, and that's where we can go between solid and liquid, solid and liquid in this case. And what we're going to be is going to be a key take-home as we move through this chapter, and we're going to start with next time, is that the stronger the intermolecular forces, we haven't really learned how to quantify these yet, but we will next time, but the stronger intermolecular forces you have, which we're going to abbreviate as IMFs, that correlates with a higher boiling or higher freezing point. So if you're going to boil a liquid, the temperature you have to go to boil the liquid is going to be higher if you have to break stronger forces between the molecules, and similar for melting. If you're going to break the forces between the molecules to convert it from a solid to a liquid, you have to go to a higher temperature if those forces are stronger. So that's kind of a little primer on what we're going to do in the beginning of Chapter 9. We'll get into a lot more details next time as we talk more about phase changes and intermolecular forces.